In our previous lesson, we had learned on how to calculate the standard cell potential, which is the E naught cell, for reaction that is at standard condition, which is 25 degrees Celsius, 1 atm of the gas pressure, 1 molar of the solution. Nernst equation. Nernst equation is used to calculate the cell potential, which is the E cell, for any chosen concentration. So we are going to use the Nernst equation if our cell, our voltaic cell, are not in standard conditions. The Nernst equation is written as E cell equals to E naught cell minus 0.0592 over N log concentration of the product to the power of its stoichiometric coefficient over concentration of the reactant to the power of its stoichiometric coefficient. N here indicates the number of electrons that are involved in the reaction. So the product over reactant here is our reaction quotient. So to determine our reaction quotient, we are going to have a look at the overall equation where aqueous phase and gas phase are included in the expression. So in this example, we already have the overall equation, right? And the standard cell potential, the E naught cell value is also given. The question asks us to find the cell potential, which is the E cell, if the concentration of the nickel ions is 5 molar and the concentration of zinc ion is 0.050 molar. So what we need to do is take out the half cell equations because we are going to find the number of electrons involved. So the number of electrons involved, which is the electron that we equalize in this reaction, is 2. So our N is equals to 2. So write down the Nernst equation, which is E cell is equals to E naught cell minus 0.0592 over N log concentration from the overall equation. Remember, the one that we are going to put in our reaction quotient expression is only aqueous and gas. So from the overall equation, we only got aqueous phase. Okay, so the reaction quotient is product over reactant. So our product is the concentration of the zinc 2 plus ion over the concentration of our reactant, which is the nickel 2 plus ion. So since the coefficient for these two is 1, so both are to the power of 1. Substitute the value and then we will get our answer, which is the E cell positive 0.57 volt. For the next example, we have a cell notation. And given the value of the cell potential, which is the E cell, is 1.198 volt, the question asks us to determine the concentration of the hydrogen ion. And also we got here the E naught half cell of the silver. Okay, so as usual, first we are going to take out the half cell equation. Okay, so from the cell notation, the left side here is our anode and the right side here is our cathode. So since hydrogen undergoes oxidation by releasing 2 electrons and form hydrogen ion, and at cathode, the silver ion gain 1 electron to produce the silver atoms. So equalize the electrons. So we have 2 moles of electron at anode. So we need to times the cathode, all the species here with 2. Alright. So the overall equation, since the number of electrons involved is 2, okay, so cancel out the 2 electrons here. So our overall equation is going to be 1 moles of hydrogen gas plus 2 moles of silver ion produce 2 moles of hydrogen ion plus 2 moles of silver atom. So the Nernst equation for this reaction is gonna be E cell equals to E naught cell minus 0.0592 over N log the reaction quotient for this reaction. Okay, so we are going to refer to our overall equation. So remember, only aqueous and gas are included in the expression. Okay, so we have on our product side, okay, so the hydrogen ion, so the concentration of hydrogen ion, the coefficient is 2, so the power of 2 divided by our product. Here we have the hydrogen gas, so the partial pressure of the hydrogen gas, okay, times with the silver ion, so the concentration of the silver ion, the coefficient is 2, so to the power of 2. So we already have the E cell value, and then we need to find the concentration of the hydrogen ion. Also from the cell notation, we have the pressure of the hydrogen gas and the concentration of the silver ion. So we need to find the E naught cell value for this reaction. So since we already have the E naught half cell of the silver here, the E naught half cell of the H plus over H2 is actually our She. So the E naught half cell for the She is equals to 0 volt. So the E naught cell value for this reaction is positive 0.80 volt. So substitute the value into our Nernst equation. So we already have the cell potential, the E cell value 1.198 volt equals to the E naught cell, which is 0.80 volt minus 0.0592 over N. The number of electrons involved in this reaction is 2. Okay, and then log concentration of the hydrogen ion to the power of 2 divided by our pressure of the hydrogen is 1, so 1 to the power of, sorry, there is no coefficient for the hydrogen gas. Okay, and then we have the concentration of the silver ion, which is 1 molar, so 1.0 to the power of 2, since the coefficient is 2. Okay, so the concentration of the hydrogen ion is 1.89 times 10 to the power of minus 7 molar. There are two factors that will affect the cell potential. We have concentration and temperature. Since the Nernst equation is written as E cell equals to E naught cell minus RT over NF times 2.303 log concentration of product to the power of its coefficient over concentration of reactant to the power of its coefficient. Okay, so when the concentration of the reactant increases, the value of the E cell also increases. And when the concentration of the product decreases, the value of the E cell also increases. So increasing the concentration of the product will decrease the E cell value. For the temperature, the E cell will increase with the decreasing temperature. So the value that we used in our calculation previously, which is 0.0592, okay, 0.0592 is only can be used if the temperature is 25 degrees Celsius. R indicates the gas constant, which is 8.314 joule per moles per Kelvin, while F is the Faraday constant, which is 1 Faraday equals to 96500 Coulomb.